Thank you all so much for joining today to kick off the new term with our seminar series. Today, I'm very excited to say that we have Nils Thuerey joining us. He is a professor over at the Technical University in Munich. Although very far away from Seattle, we are still able to host him virtually today. He's going to be talking about some really exciting work at the intersection of partial differential equations, computational mathematics, and machine learning, and in particular, how we can create differentiable simulations. So with that, I think I'll go ahead and turn it over to you, Nils. Again, thank you so much for being here, and we're looking forward to your talk.
Thank you very much for the introduction, and thanks again for the invite. I know the title sounds very far-reaching. Here it's talking about paradigms, but I want to talk about a topic that has been keeping my lab busy now for several years, and that I thought it's actually that is worth revisiting or looking at from a bit of a broader perspective, and that's what I want to focus on in the following. And yeah, I should mention here also for the background and so on, I did get help from Gen AI approaches. I'll come back to that also in the context of differentiable solvers in a moment. Yeah, let me start very broadly. We're targeting PDE solvers. Partial differential equations give us in a way a great language or formulation to work with effects that are all around us in the natural world. And there's a vast range of applications, but an important one are fluids. Probably many of you are aware of this, but just to point it out right, the air in the room we are all sitting in over there and here, the blood in our veins, our bodies are made up of a large portion of water. Liquids as well, of course. You have two fluids suddenly with an interface.
Are you sharing that PowerPoint with the whole call? Oh, I'm sorry. I'm just looking at the wrong thing.
Yes.
Go ahead. Sorry.
Okay, is it visible? Okay, yes. And there should be some videos here. I hope it's showing up. Airflows are also a classic topic here, right? Blow around in airflow, what's keeping the plane up in the air. So there are many important topics here. And right, I used to find it very necessary to motivate people to actually consider this combination of PDE solvers and AI. By now, I think with all the Turing Awards and Nobel Prizes, it's been more and more clear that there's an interesting technology that's at least worth considering. I think it's actually quite powerful already, but it's definitely also, it has controversial aspects, and where it's really going to work out is open, but I think it's an interesting direction and topic to explore. The larger scope here is how can we use these techniques to better solve these PDEs, to better understand, to better predict what's happening in the world around us. One also fundamental distinction I want to make at the beginning is between different approaches here. And first of all, right, it's worth mentioning that foundation models are, of course, a hot topic here. I kind of don't really want to talk about that. It's an interesting connection. Nonetheless, I'd be happy to discuss. I want to focus on these differentiable solvers, which are in a way less fancy at the moment. But I think because of the longer time people have been looking at this, I think it's a good time. And they're actually by now, there are all kinds of interesting opportunities here. So I would argue it's, despite not being as prominent at the moment, it's nonetheless a very interesting and promising topic here in this context, just to point this out. And also, in a way, I think it's a very good time to talk about PDE solving, scientific and AI, because I think we're at a good point right now where there's really, we're in a step where all this can have real-world impact. In the past years, I think this has been quite difficult, but now we have methods that do actually scale. And one more reason to discuss this. Right, here. Now I want to make this distinction. You can distinguish what I would call a surrogate, a learned surrogate or neural surrogate, where we put all the work onto a neural network, right? That's behind all of these AI approaches. So that's indicated here by this orange blob. I want to contrast this with the right-hand side, where we have a neural network, also in the loop, right? There's still this orange component, but next to it is a classic numerical solver here in the form of this blue box, and they're working hand in hand. And the solver stays there, so we're not replacing it. For the surrogate, essentially, we're replacing the numerical solving process. On the right-hand side, it sticks around. And I think that's one way to distinguish approaches in the field. Both of these are not new, right? So there are many interesting works on both sides of this. The right side I would call a hybrid solver, but also have all kinds of names around here. That's important to keep in mind. So we're using neural networks, but they're not the only component, and some form of numerical solver will stick around. Right. Another distinction is for the learning tasks, you can call these prediction and correction tasks, right? So depending on what goal the neural network has, the learning tasks change. And I'll come back to that in a moment, looking at. So these prediction correction tasks directly are a direct result of these different formulations. Also, worth mentioning here, I won't be talking about pins, just to make it clear, right? There's a solver in the picture. There are some similarities and differences to pins. I'd be happy to discuss in more detail, but because this was a common question in the past, so none of the things I'm going to show are actually using pin methods, just to make it clear. Let me introduce a bit of notation. Focus on the big picture, but nonetheless, I think that's an important point. So we have a partial differential equation, right? The sum function of derivatives here as a time-dependent PDE given at the top. And so some temporal change is given by a bunch of higher order spatial derivatives. This could be Navier-Stokes or Burgers or some other equation on a computational domain with respect to a function u. And now I'll primarily actually look at time-dependent problems. So we have a mapping from some initial state towards later stages with a operator g here. And in the simplest task, actually, that would be such a surrogate. We're trying to replace that PDE solve, which in a computer which tackle with some choice of numerical methods with a neural network. And here the numerical method is replaced by this neural network denoted by the F with some weights theta. In the simplest case, looking at a single time step, you would give this neural network one state u and let it produce the next time step at time t plus one. Also worth noting here, so these tildes on top should indicate that here now we have an approximation. But like a numerical approximation, our neural network will also introduce some errors and most likely not give us the exact solution. Just to make it clear, we might have a computational grid can actually be as complicated as necessary. So here's also some non-trivial multi-block mesh around some spherical obstacle. And this solution at time t could now be a point in this grid that we provide to a neural network. And on exactly that same spot, the neural network could be tasked to predict the next value of our field u at this point in our grid. And then, for example, this could be the form of a convolutional network. So you could apply this network repeatedly to get the solution everywhere in a computational mesh. But also the neural network architectures, I'll not go into much detail. This could be any kind of neural network backbone or also mesh representation. Yeah, the goal, of course, is to approximate the solution there. Now, typically, the learning task here could simply be, we have a typical input output relationship here. So instead of dealing with these u quantities over time, you could say, well, the network basically gets an input x, for example, a time step to produce the next one, the form of a y. And in this example already, we actually have a numerical target produced by a numerical method. So we could include a similar numerical solver. The following, this will be denoted by this p operator that gives us an approximation of the output of the y. Now, if this is a good one or a sufficiently good one, then we'd basically be done, right? Then this solver would give us the whole answer. However, especially if this solver is approximate, meaning if we, for example, reduce the spatial or the temporal discretization, potentially it's faster than the one that generated ground truth, for example. And imagine doing a high-resolution DNS solve and now switching to an approximate, right, low-order approximation of a similar flow. Then there's a certain gap between the outputs of the numerical solver and the ground truth we like to achieve. And this remaining step now could be an interesting learning task. And in this case, you'd actually have a numerical solve and on top a neural network. So this would be going towards the hybrid solver setup that I mentioned earlier. To come back to the title of my talk, right? You see, Navier-Stokes is a good example here. We could have a reference with the high order discretization and then switch to a lower order for the combined learn method. Now, as mentioned in the title, what I'm interested in the following are solvers where we can actually compute a gradient. So we have a derivative of the output of P here, the Y essentially, with respect to the inputs X. This is a Jacobian matrix, as I'm sure many of you are aware, right? In this case, it's square because X and Y would have the same dimensionality, but it's a big matrix. We're essentially dealing with first derivatives for each in and output quantity. If you, for example, consider the whole state of a grid, this could be a big matrix, but in a way, it's not a very complicated quantity. And that's actually the one that's also driving all the machine learning algorithms, right? So typically we have a loss at the end, which means if we combine this into scalar value at the end and then look at these Jacobians, that actually turns it into a vector again. That's why also in deep learning, we're typically talking about gradient-based methods, not Jacobian-based ones. But right, that all comes from the scalar loss formulation. And luckily with AutoDiff and the current setups, all we need is actually this vector with respect to X in this notation, not full matrix quantities for computational efficiency, but this quantity in line with what we learn for a numerical solver, this is actually, in a way, the key ingredient that will make the following examples work. And as already, I hope got a bit clear from this overview here, this is what happens in learning. Right? I don't want to go into all the detail for typical learning and gradient descent methods, but essentially, we're here expecting that the solver itself can work similar to a layer in a neural network API and provide a first derivative. This is standard for learning, right? So here is actually just to make that clear a bit visually. We typically have these lost landscapes, or dealing with an energy function, trying to find a minimizer for that. The gradient is a well-known quantity, points along the perpendicular to the isolines of our loss, right? So in a way, it's also a fairly well understood quantity for convergence, of course, being first order, also having similar problems as encountered in other fields. But nonetheless, this picture and the alignment of these calculations makes it very easy to integrate numerical solvers into the learning process in this way. Now, there are all kinds of ways to call this, right? We've in the past often called this differentiable physics to distinguish it a bit from differentiable rendering and differentiable other processes. You can all summarize this under differentiable programming, like many of these learning methods currently operate. And in the end, actually boils down to doing an adjoint method via backpropagation. So, right, there are many ways you could call this, but right, I'll be talking about typically differential solvers or differential physics in the following. And to stick a bit to this level of intuition here for a moment, one nice way I like to think about it is in terms of the kind of system introduced by Daniel Kahneman. Has anyone read this book, Thinking Fast and Slow? I hope some have come across this. Very nice book that does not deal with neural networks at all. But in this, he explains our brains working basically in two different modes. One slow analytic process when you sit down with a piece of paper and a pen and work something out. And what you're doing right now, right, looking at a screen, listening to something that's very fast and intuitive. And especially the second process is actually what also neural networks are really good at doing at the moment. And the slow analytic process, the system 2, he calls it, this is in a way, I think, similar to classical simulations that provide certain guarantees that have well worked out properties, but these can be combined or nicely do combine with neural network components for system 1 evaluation. And because I'll mostly be considering time-dependent things, the simulation foundation could basically work on a simulator and then for each of the steps along the way be combined with the neural network. So just for an intuition to motivate this combination. Yeah. One distinction we can also make here is difference to classic adjoint methods is whether we first discretize and then optimize, or discretize first and then optimize. So classic adjoint methods, we actually would write out the whole formulation for your optimization problem to solve a certain problem. This turns out is more difficult once you want to change things. The nice property of this current deep learning toolbox approach is that we basically work with discretized operators that we can combine, and then via autodiff or so, we directly get a flow through these different operations with corresponding gradients, which also lets us optimize. So I think in this current landscape, basically this discretize then optimize viewpoint is a very nice and attractive one, and also that's what I want to use in the following. Right, nice thing is still you basically get analytic gradients. The gradients are accurate. Right, you just chain them together with a chain rule, and it's working on the level of these basically formulated operators. So the first approach to first optimize can have advantages for certain formulations, but it can be also, it typically becomes quite complicated for non-trivial equations. And this deep learning viewpoint is quite neat in terms of the flexibility. Yeah. Also, if you do this backpropagation, you can basically trace a chain of operations that you do in a forward pass back to any parameter. So I have quite a few examples that work with these states, like a flow, you as mentioned before, but you could basically work through this chain and then compute a gradient also with respect to a material parameter or some other quantity, just to point this out. Let me motivate this first kind of learning task in a bit more detail. I mentioned these surrogates, where we basically focus on what I would call a prediction task, where no solver is in the loop, in the picture. So just to contrast this later on with having a solver, it's actually quite straightforward, right? We have these states U over time, starting with an initial one, and then we're applying, if we already have a learned surrogate, this F repeatedly to produce new states. If we have a reference, we can compute a loss for each of these states and then train at training time, change our parameters such that our neural network outputs these desired states. So in a way, this is a pretty simple process. What already comes in here is that the same F is evaluated repeatedly on its own input, right? So I hope that's clear from the chain. This first UT or U0 could be a pre-computed one from some external solver, and the later ones here now come from the network itself. So that's what I would call unrolling. This turns out to be actually quite neat for doing time-dependent phenomena. And one important application here is already that these U's here now come from the neural network solver. And if you imagine a training time, for example, this F might be, especially initially, quite bad, right? So the U here that you get might look very different from the ones that are produced before. So it's not trivial to learn. Also worth pointing out here already is that the gradients here flow through basically flow through the F multiple times, meaning we're also applying these derivatives, the Jacobians that come from F here, and the operations happening multiple times. And right, the accumulation of errors from our F typically mean that the states evolve quite differently. In this very simple example, it might not be too bad, but looking ahead towards more challenging tasks like fluids, Navier-Stokes, for example, with turbulence, this is potentially, this can be quite tough. Over longer time spans, we typically have some terms that will grow exponentially here, right? If you imagine the Jacobians are multiplied up here in the end for the chain rule, if there's any component here that is reinforced, it's basically will grow, well, it's high likelihood that it will grow exponentially. If it's less than 1, of course, it would be dissipated. That's not too bad. That's more stable, especially explosions can be more difficult to deal with. And in the long run, for flows or any chaotic system, right, we're dealing with chaotic systems. So even tiny changes can really blow up, the classic butterfly effect. And latest on that scale, right, if you're going towards a chaotic time scale, then also the information you get from such a back propagation will most likely be noise. Right? So you most likely won't be able to learn much from an unrolling chain that ends up in chaos. Just to point out, even with the simple setup, there are some interesting aspects and challenges here of learning from this and learning, letting a network learn from these roller chains. The next slide here should now illustrate, especially one of the fundamental ones, I think, is especially that unrolling the network produces something different from the target, or potentially anything that we can pre-compute, right? Because the data produced by the network comes from the training, it changes over training time, and this is a classic data shift problem for machine learning. The distribution of states, what the network is trained on, right, and what kind of learning signals it gets, changes over time, and we really cannot pre-compute the data here. This is inherently coming from the network itself and the process. Just to also visualize a bit here, this is potentially really a challenging environment. So far, it's only been a network in a way as simple as possible. But if we now look at this other kind of task, the correction I've mentioned before, where you have the solver in the loop, it looks slightly different. So now we're bringing back this some discretized version of a physics solve and basically just put it in the chain. So we have the U in the simplest case that's provided to the solver. Then the output goes to a network. Also, in the very simplest case, it just has an additive correction, so it just modifies the state U with some addition. You can think about more advanced ways of combining these outputs, but in addition, actually turned out to be a very good starting point in many cases. And now we can basically do the same learning task to try and train the network F now to bridge the gap between what P produces and what our ground truth is, And a good picture to have in mind here is the aforementioned one, that we have data from a very expensive, high-resolution PDE solve, and the solver that we have in the training here is something very approximate and fast. Now, right, it's worth looking at the little green arrows now. Those indicate the chain of backpropagation. The black ones are the forwards pass, and now if we evaluate the loss, we have the ones that go right from the loss evaluations back into the network. And the reason why I have these two steps is now that finally in this setup, we actually do need this differentiable solver. So far in the other examples, this was not really playing any role. And if you also look at the left half here, if we only unroll one step, then in this scenario, you would not need any differentiable solver, because the loss only backpropagates right from the loss evaluation into the network. So this would only flow through the different layers of the network, but this is what produced the output. So this would not involve the solver at all. For the second step, however, we now do have a path that from the loss provides a first gradient to the network, but then continues through the solver to provide essentially feedback to the network how the output of the first step, the first call to the network, changed the result of the second one. I hope that's visible here. And so from the second loss, now we actually go through the solver once into the first network to provide feedback about how the physical solve in this case interacts with output, and how the network should adjust, at least in a linear level, its output to match the target. Yeah, this is a very simple setup. It's only for two steps, but these terms basically go quadratically for longer chains. So you basically get the whole chain for each additional step. So a lot of Jacobian terms here add up, and also a lot of gradients from these different loss evaluations are combined. But for this time unrolling, all of these together give us now one update of the network. Basically, it's one step, one change of the theta. And then we could continue with a new mini batch or so to evaluate this whole forward chain again and get another learning signal for the network. Yeah, so much about these different tasks. So this is now the correction where we really have this combination of a differential solver and a neural network. And here's we can finally show some results. This nicely can be trained with this integration. Here we looked at a two-dimensional case. It's a relatively simple one, but well understood. A shear layer in a flow. This is the case in motion. I have a ground truth on the. No, I don't think I have any ground truths. Okay, if you're interested, I can show you ground truths. The top, I hope you can believe me for now, is already pretty close to the ground truth result. In this case, the solver that is called here, this is already the hybrid solve, is the approximate solver and the neural network, would not resolve any of these vortexes being shaded nicely. But now in combination, they actually do develop. And at the bottom, you see a bit also where the network basically applies forcing in terms of vorticity. And you can see that it's nicely localized around these different vortices in the flow. Because it's a relatively simple, well understood case, we can now analyze this in more detail. And just to point also out, here we really have this combination of a coarse Navier-Stokes solve. It's a second order piezo solve in this case, but nonetheless with a pretty coarse spatial and temporal resolution. And for each of the steps, there is a neural network additively changing the solution. And this is really happening over time. Now, this being a classic case, we can look at some typical evaluation metrics. For example, energy spectrum for flows is a good starting point. Here you can see the no model version in blue, the DNS, the properly resolved data with these orange dots, and then different neural networks in green. And these spectra are actually very aggregated, so the differences don't even show up so clearly, but here nonetheless you see a clear gap between the blue line, right? So the base solve that's in the loop here is pretty bad. All the other ones look pretty good, but if you now look at different quantities, like here the Reynolds stresses, indicating the amount of mixing going on in the flow, that now also shows that the light green version, which is the one that was trained with the most unrolling, this was trained with 60 steps of unrolling for every step of training. So it was fairly expensive at training time, but this really now also matches the statistics and the properties of these targets. A nice side effect also of the unrolling is that this is really pretty stable for long rollout periods. In this case, this was over 2,000 steps of simulation for a simple case. But nonetheless, I hope it's the first indicator that that this is an interesting technology. We try to, there are more benefits to this. Of course, the question now is, this is all synthetic data. What do you gain from the combination? And because we have a solver in the loop, we can actually run the same solver on the same hardware and do a fair comparison by lowering the accuracy of the reference to that of this learned solver. Nonetheless, on that level of accuracy, or on a similar level of accuracy, basically, the learned version is faster, trades in generality. So it's specialized on, in this case, really the shear flows, but nonetheless, we observed a nice speed up here. Now, another interesting implication of these differential solvers is that it basically allows you to go from training pure surrogates to correction setups. I would argue basically if you reduce the discretization and the cost for the numerical solve enough, it's not overly expensive. You need to run it at inference time basically. But what this comparison here indicates a bit is that as soon as you have a solver that can do something useful, as soon as this P operator that was on the previous slides does anything towards the goal that should be learned, it intuitively makes the task for the network a lot easier. So we studied this a bit more broadly across different architectures and across different PDEs in a follow-up paper. And these two graphs are from a Kormo-Zivashinsky and a Kolmogorov flow here, left and right, both convolutional, but we also had graph network results and over many hundred different trained neural networks, and along X you see different neural network sizes, decreasing the error. The main point here is that there's always a big gap between the correction and the prediction result. So if you don't have a differential solver, if you cannot train together with your solver, then you're basically stuck with pre-computing data and doing this prediction task. But if you can integrate the solver, basically take some of the load off of a neural network, then we saw consistently across different PDEs and different settings very significant improvement. Here, this is a log scale, so it's sometimes more than a factor of 10, but on average, it was actually an order of magnitude that you gain in terms of here relative error accuracy towards the ground truth results from the combination. So this is a nice improvement in accuracy, I would argue. Now, there is an interesting aspect here, right? So if you get 10 times more accuracy, the question is, why don't you do this more often? Which is a good point to discuss the disadvantages a bit. So these differential solvers are not that widespread, right? It's so far, admittedly, not very common to include a full numerical Navier-Stokes solve into learning. Joint methods, in a way, have been around longer, but computing these gradients, it's getting better, I think, but it's not a standard feature. If it's not well supported, you might also lose a lot of performance on the interface. So that could increase the computational cost at training time. And admittedly, this is one of the challenges for this combination. But nonetheless, again, here, one of the reasons to advertise this a bit more, I think it's improving and has a bunch of benefits. So I would hope that also the next years do bring more and more solvers that provide this functionality, but it's definitely at the moment not something that should be taken or can be taken for granted. Yeah, we've worked on a bunch of kind of proof of concept solvers here. Also for example, for SVH particle-based flows, variety of other interesting methods that have been developed over time. One of the recent ones from our lab that I want to mention here is what we call the PICT solver. So this is a block structured grid code, still this P, so a bit similar to before, but now flexible and with some mesh refinement. And this is one of the newer results from a similar correction task to before, but now for more interesting 3D flow. This is a channel flow, so we have a wall basically that sheds turbulence. Still a well understood process. So here we are basically still aiming for the same goal of matching a high resolution DNS solution. For this channel flow, there are very good spectral solvers around. So now we basically turn this task around a bit. Instead of being supervised step by step with specific states, which, as mentioned before, for chaotic systems also becomes dubious or very noisy for longer time spans. Here we try to, similar to some of the previous reinforcement learning approaches, directly match turbulence statistics. So you know how the different moments of the velocity fluctuations should change on average away from the wall. We can get those from a well-resolved, in this case, a spectral solve, and then say this combination solver should directly match the statistics, this function of how the different moments of the distribution should vary. This is the reference solver in this case from this work by Hoyes et al. For now, this is what I'm showing here is a single wall Reynolds number, but it's actually interesting or in the works to generalize this a bit more. Here's a small video on the right side with a cut on the sides, and you see the vorticity closer to the wall. So it's a channel flow. In this case, the view includes both shows the bottom wall, but also includes the top wall for this cutout. And what turned out to be quite important here for a proper three-dimensional turbulence case is this unrolling aspect. So basically training with the time evolution of the physics and the consideration here for the neural network. And as mentioned before, the back propagation can be both a bit tricky in terms of the buildup of Jacobian components, and it can be computationally expensive. So for this paper, what turned out to work quite nicely is to do a combination of really unrolling and back propagating through a full chain and exposing the distribution, addressing this distribution shift problem by doing a certain number of warm-up steps without gradients. So it's a bit this picture from before where we have certain steps that don't have a gradient. We can see it here, these green arrows are missing. For this specific scenario, I think what we did up to 69 of those steps to basically really at training time see what the solver and the combination of the learned component and the solver produce. And then we do a certain number of steps that are fully treated in terms of back propagation. So we're also over the course of multiple time steps, the network gets a signal how its actions, basically how corrections work out over time. This is just, the numbers don't matter too much. This is specific for the turbulent channel flow case, but at least including a certain number of not backpropagated steps turned out to be really useful here to achieve this temporal stability and also the accuracy here, because there is a strong data shift here, and this is a fairly tough task. So just to summarize it here, so we're dealing with a correction task, right, with a non-trivial, in this case, spatially adaptive second order Navier-Stokes solve. The network itself is super simple. It's still a very, very small convolutional network, and a loss in terms of the statistics from the spectral solve. And this is a qualitative picture showing the reference a bit. The low fidelity inputs are only the solve, simple turbulence model for comparison, and the learned one. But what I think is more interesting is this plot here. So these first two, the low fidelity and Smagorinsky resize, are the orange and blue curves at the top. This is now a loss that essentially measures how close these statistics on the reference are matched across the different components, different XYZ directions and first and second order moments here. And at the bottom, there are different learn variants. And the most important bit is basically this is more than an order of magnitude lower. And these are now eddy turnover times. So 30, and in total, I think almost or around 20,000 steps of the simulator. And this indicates that the network can actually preserve or improve the turbulence statistics for very long time steps, even in this now really nicely chaotic three-dimensional context. If you look closely, actually at the beginning, you also see a dip. The very first few frames work especially well, but this is exactly what the network was trained for. Afterwards, you can see it as temporal generalization. The network did not see those really long rollouts, and it does worse there, but nonetheless, it preserves a lot of the important features and of the statistics here for the turbulence over time. And basically also this doesn't break anymore, so you could keep on running this. This produces a very stable learned corrector. In this case, thanks to the unrolled training. I do want to mention, also in this case, we can make a performance comparison, and we still see a nice speed up. I do want to briefly make the connection to generative models. I would guess or hope that quite a few of you have heard of those, like the diffusion models, diffusion flow matching and co, where we basically have a stochastic network that works with noise and can produce different solutions. And in this case, also, these differentiable solvers actually do have nice capabilities, and that I do want to briefly, given the time, highlight. So for these, we have this process, the first forward process that destroys the signal, and then we have basically a denoising network that should restore it. And for these denoising, this is again where we can now integrate a solver to improve the kind of physical accuracy with respect to some constraint or PDE, some known prior for the data, as an interesting add-on. And one particular, maybe more as a look ahead. There are two options here where to use the physics solve, either at training time. So when this diffusion model is trained, you can actually let the physics model provide gradients basically for the model itself to produce a better state at training time. This also requires differentiability because the gradient need to go from an output back through the physics constraint into the denoising model, or you can invoke it at training time, right? You basically modify the model. At inference time, you can train the model without being directly constrained, just for the generative process. And then when using the trained model, you can still invoke this the physics constraint to basically improve the denoising process. The first one is essentially more expensive because you need to run the physics constraint after training at inference. The other one, if it works well, gives you a model that's as fast as a pure generative model, but increases training time. So it's a bit of a trade-off. We also noticed that there's there's some conflicting goals here. One is really getting the right distribution in terms of a probability distribution for the model, versus matching physics constraints with a mean or so very accurately. And if you overdo it, you quickly end up in a deterministic mean solution that nicely satisfies the physics constraints, but loses its distribution. And one of the cases that nonetheless did work nicely for us was this one. This is, although the outputs here don't look too complicated, this is a fairly non-trivial dynamic stall case for propeller blades, basically. And here, also a normal regular diffusion model actually gives pretty good results. But if you then combine this good model with the physics constraints, you get a nice factor of improvement. Right. If you're interested, I'd be happy to explain a bit more about this combination. But I want to leave it at this outlook that these differentiable physics components are nonetheless, even for more recent deep learning developments like these generative models, are actually very nice add-on and combination. Yeah, that brings you to some conclusions. So, right, I focused on these differential solvers here. It would be great to bring this back towards foundation models or working with large pre-trained models. I don't see any hurdle here. It's going to be an interesting outlook, but nonetheless, I think the differential solvers by themselves are really interesting and potentially powerful component. I've not really mentioned a couple of other advantages, like it enables direct optimization tasks with classic methods, right? You could directly do a Newton optimization on the outputs and other nice things that are not necessarily easy to do with classic solves. And to come back to this larger picture from the very beginning, I do see a nice future here where we basically have more or less arbitrary combination of both learned components and classical numerics. If we have differentiable pieces, then it's really easy to combine this and preserve this larger picture, just like you would do in these examples within a deep learning framework with auto differentiation. I think this could potentially be very flexible. You could imagine a base solve that is augmented by different learned components to improve certain aspects, depending on accuracy, depending on demands or applications. But I'm quite certain we're going to see more and more of this in the future. And yeah, I think it's actually worth keeping that in mind when now thinking about the next generations of numerical solvers and tools to be developed here. And with that, right, I hope I was able to show a bit. These differential solvers do provide a very neat integration, a nice range of applications, and also, for example, with these generative models and the probabilistic capabilities, I think they are really exciting applications and features that we can get from the combinations. If you're interested in more, nonetheless, a word of caution. So I do like to show this classic simulation. There's definitely work left to be done in terms of scaling. Right now, it might be pretty obvious from the examples I've shown. We are away from really large scale simulations, and this is now another pure simulator result from a lab that is just in a way just a very nicely optimized and well working solver working on a single machine without any AI or other techniques, and here simulating billions of particles. So the classic techniques are also very powerful. It's worth keeping them around, but nonetheless, if we could leverage this as a basis and then combine it with AI, I think They're really an exciting range of possibilities. And if you're interested in some more of the basics, also code examples, I can recommend our website here that includes a bunch of Python notebooks and some of the topics I've discussed here. And also thanks to the students who actually did all the work here. So Björn, Giacomo Chang, Liwe, and Benjamin. And thanks for listening. I hope we have some time for questions at the end.
Thank you so much for that really great talk, Nils. I think we have some time for questions, so we'll start maybe locally in the room with me. Are there any questions here? Yeah,
I can ask. I'm wondering if you also looked at SGS modeling or adjusting solver or augmenting solvers with a corrector neural network for unstructured meshes, or because it seemed like the ones that you showed were regular. Well, I'm not sure about regular, but finite difference solvers. Have you thought about adapting the method to other?
Yes, we have looked into this. There are some ongoing works. This basic idea of having or working with a differential solver is not restricted to the structured meshes. So these examples I showed before did use a deformed grid. So they did have adaptivity also for the boundary layer of this turbulent channel flow. Was not really visible from the pictures I've shown, but this went beyond a regular grid at least. But this would, or it seems to work just as well on unstructured meshes. Right. The caveat being you need a differential unstructured solvers. There's some nice works, for example, one from Romit Maulik's group on leveraging, I think it was with OpenFOAM. It's a bit this question of how do you best interface, and right, for graphs, potentially this is actually it does become a performance issue, but there's no conceptual or fundamental problem.
Thank you.
Yeah, and also we want to open questions up to anyone on Zoom. I saw there were some comments in the chat, but I don't think that there was a particular question from it.
Okay.
Oh, sorry, yeah.
Hi, Nils, thanks for the talk. Maybe I can ask a question on resolution. It seems on one of your examples, you had like a coarse Navier-Stokes solver in the loop, and then you have some convolutional network that will act as a correction to give you an equivalent solution as a high-res simulation. But is that solve represented on a fine resolution mesh, or do you essentially pull it back to a coarse resolution mesh to give an equivalent representation?
Right. It's on the coarse grid. It's like like SGS modeling, like coarse graining. So trying to represent the fine resolution or integrated quantities from the fine resolution on a coarse grid.
Thank you.
Right.
Yeah, and it seems there's a question on Zoom. Chris, can you come off mute for that?
Yes, thank you. Hi. I guess I understand that mesh resolution obviously plays a major role in determining the quality of a numerical simulation. Obviously, it also contributes to the computational expense of many of these CFD simulations. I often hear the term meshless being applied to either physics-informed machine learning or to neural CFD, and I'm wondering, is this just a buzzword? Is it actually even possible? What does that actually mean in context?
Okay. So meshless, there are also meshless simulations. There are actually a few like SPH particle-based ones that are sometimes called meshless, where you basically have smoothing kernels or interpolation kernels on particle clouds to solve Navier-Stokes or other problems. In the learning field, there are all kinds of approaches by now, and also neural operator this neural operator viewpoint that you can basically sample your solution, right? You have frequency-based referencing. You can sample it more finely in between evaluation points. I have to admit, in this context, I didn't come across too many works that really claim meshless properties. Also for neural operators, typically you do have some support points or some points where the evaluation is actually done. Neural fields, which actually is going towards this pin-like direction, basically represent your solution with the neural network. There you don't really have a mesh. It's more of a composition then of the neural basis functions that you can evaluate. So this you can see as a meshless method. It's a neural field viewpoint. Those are then pretty expensive to evaluate typically, because every sample that you want to obtain at one single position means you need to go through a whole network. And so
to the point that it might actually be more, there might actually be not much of a cost advantage in terms of computation to do it.
Right. It's in a way, it can be powerful for compression. You might get a very reduced representation, but to work with complex things in higher dimensions, space and time, it becomes really tricky.
Okay. Thank you very much. Thank you very much.
Our examples typically don't make use of that. Yeah.
Cool.
Right. We have a few more questions, and we'll go in the order that I saw them. Is it Ame has a question?
Yeah. Can you hear me?
Yes.
Yeah. All right. Great talk, by the way. I'm a PhD here at Cornell, and I work on gradient-based model reduction for control. And so in my work, I do a lot of like optimization stuff for gradient evaluation, which is something you did talk about. And it turns out for a lot of these like non-convex optimization problems, they are very like sensitive to initialization. So initialization of the parameters. So how do you work around that?
That's a very, very good point. Optimization problems, or I would generally call it inverse problems in this context, are typically very nonlinear. And if you would do a classic gradient descent or any classic optimization approach, right, just based on a classic solver, on a differentiable solver, you could apply LBFGS or something in the easiest case, right, and try to solve it. And this is super difficult because of the typically very nonlinear energy landscapes. You easily get stuck in minima you would not like to get. The deep learning frameworks here are quite neat. Typically, the stochasticity, especially in deep learning, does solve at least some of these problems, where you basically approach the solution from potentially many points. And from our experience, what does work quite nicely, or what I would recommend also as a starting point, is to ideally combine it with network, at least for an initial guess, a rough estimate. And then you could follow up on that initial guess with a classic optimization. That can help, right? It's with nonlinearity, it's difficult to give very broad guarantees, but that can help on or at least reduce the chance for getting stuck. It still gives you guarantees of a classic optimization scheme, and also does benefit from actually backpropagating through both of them. Right, so that would be a recommendation here from my side.
Yeah, thank you.
Great. And then Yong-Hoon.
Oh, yeah. So I'd like to ask you some high-level questions. So I think the current AI system handling the discrete time data or the simulation to the AGI, I believe that the movement to the continuous time system or the data simulation would be so important. So do you think that this kind of the neural ODE or the PD solver will be the right track to solve that problem? Or do you think the way to approach that kind of problem?
Right. It's also a good point. The examples I've shown are definitely still simple relatively simple on these fronts. Also, the 3D example I've shown did use a discrete fixed time step. The time is actually relatively easy to account for. if you would use different time steps and potentially include a DT in the valuation, this could be handled. We also do have tests that work with different grids or different meshes. So I think it's actually solvable. It's also with recent, especially recent architectures that scale up, we can handle these fairly efficiently. You do need to basically include a training time. That's one of the key things we noticed. If you train a model for something that was not varied at training time, and then later on you vary it, that's exactly what works well in deep learning. It will vary. There's a very high chance it will actually find that out and overfit to this. So if you want to use it for different measures and continuous time also, it's crucial to do this at training time, to train the model for it. But I do see no reason for why this would not work beyond computational resources.
Got it. Thank you. But overall quick question. So I think that handling the continuous time system currently, I think kind of interpolation between the two or multiple the discrete time data. So I think that is a little bit different handling mathematically the continuous time system and the discrete time system, right?
Okay. Yes, I was thinking about basically just continuous in terms of varying time steps, but you're right, having really a very accurate or potentially in the limit fully continuous evolution over time, that would be challenging. Yes.
Thank you for
I was mostly targeting varying time steps. I think that's not too difficult to do, but if you need a very high accuracy for over time, that would require potentially something else.
Got it. Thank you so much.
There's a couple more questions, but I also want to be mindful of your time, Nils. I know it's pretty late over there in Germany. Are you okay with a couple more?
I'd be happy to continue. Yes, for now. Thanks.
Okay, great. Then Alexander, do you mind coming off mute?
Yes. Can you hear me?
Yes.
Yes.
Okay, wonderful. Thank you. I'm a PhD student in Tennessee. I'm also working at Oak Ridge. So I'm primarily interested in neural scaling for large-scale spatiotemporal systems, things like weather cosmological systems. So I have, I guess, a two-part question. So you mentioned this a little bit at the end of your talk on scaling up, right? So what work have you done on computationally scaling your work?
That goes a bit towards this foundation model direction. So I think right now one of the key advances in the field were those transformer architectures that also power all the large language models. Also from the hype on that side, actually really well supported. We also have a PDE transformer, which we now internally use for many of our experiments. And right, I think this is working nicely. So with the right architecture, you can really train very large models now. So I think this is a key ingredient. These examples here do not yet use this, but I think it's a natural combination.
And are there any specific challenges when it comes to integrating a hybrid approach where you're still using some classical simulation to inform those in terms of scaling?
So as far as we can see for now, beyond resources, we didn't encounter any fundamental problems. So right, also exposing time and this unrolling and joint training is important. But even with the larger models, I think the changes, the picture does not change fundamentally. For now, all right. Also, scaling right now, for example, GPU memory is definitely a major hurdle. It's super expensive, and right now even the large ones only have 96 gigabyte or so. So working with 3D simulations over time is an engineering challenge. So I don't want to guarantee that if you really scale this up to super large cases, it typically does become more challenging, but at least with reasonable factors of 10 or would also guess 100, this doesn't seem to change too much.
Yeah, I agree, at least for my work. And then I guess one other thing. So we also look at weather models and stuff like that. So For those, something like uncertainty quantification is really important. Have you done any work in using uncertainty quantification to improve some of your models and their results?
So uncertainty is one of the reasons why I wanted to mention also the generative modeling. From our experience, that's a really neat component. And by now it's also, I think it's starting to really be popular for weather modeling. So I think I would recommend that, and I think that's super promising. You
Okay.
really get a distribution of outputs, and potentially then you can actually also it's relatively easy to estimate the likelihood. You can get estimate uncertainties from that, or try to sample extreme events, things like that. So generative models, I think, very promising also for weather and climate.
Okay.
Training them
Thank
is
you.
another challenge, right? You need potentially
Yeah.
good data for the whole distribution. I think that's a major challenge.
Yeah, definitely. Okay. Thank you.
I think that there's 3 more questions, and then maybe we'll call it. In the chat, Nick said that he had a question. Nick, are you able to come off
Yeah,
for that?
yeah. Just wondered if we have a non-differentiable solver, is Taylor series approximation typically used to make it a differentiable solver? Like a first order, second order Taylor series approximation, or is that not applicable?
No, this is a topic, interesting topic, good that you mentioned. Basically, right, you can approximate gradients. You could even train without the gradient and still do things like this unrolling. So there are different ways to produce in-between methods. The ones I've shown typically use the full gradient, which is also non-trivial, but gets you closest, closest to the real energy landscape that you're learning for. As soon as you do approximations, basically your gradient does not match, right? Does not integrate up to the energy landscape. You have mismatch between your forward and backward paths. That can cause challenges. So in a way, it introduces another error at learning, but it's possible. You can approximate it or also modify how you compute the gradient.
Yeah, because typically Taylor series, Taylor approximation has been used like in decision trees and XGBoost, and if you have a non-differentiable loss function, you would go Taylor series, and then you get a reasonable gradient approximation.
Yeah, right.
Okay, and so it can be done. And the only other thing I had was in the P notation, P was followed by little f, the neural network function. I think the activation for the neural network function has to be also differentiable. Both P and f have to be differentiable.
Yes, I think that sounds correct. Exactly. This whole chain needs to be differentiable. Yes.
Right.
I was assuming that the neural network component, chances are high if it's used for learning that it's differentiable. But you're right. Everything between loss and your parameters.
Yeah, the activation function, tangent or sigmoid or anything that has to be active. Yeah. And surrogate gradients is in spiking neural network, because I've worked where, it's the activation function for spiking neural network is not differentiable, but to train it with backpropagation, you would actually play a game where you mimic. You said the activation is actually a differentiable step function or something like a sigmoid.
Oh, this non-differentiable.
And in the backward pass, it will work, even though intuitively it's a different network. You have a different activation function. It's not a delta, but I guess surrogate does work in that case.
Yeah.
Okay, thank you.
Great. And then I think Trevor is next, and then we'll end it with Pavel.
Hello. First, thank you. What a great presentation. So I'm a MS student. I come from the engineering space and I'm new to the AI space. So this may be somewhat rhetorical for the non-layman's on the call. That said, in the beginning of this presentation, you said that the PDEs had a vast range of applications, and we focused on fluids today. Specifically in your presentation, you talked about generative models and how noise destroys signal, and that these solvers somewhat improve the accuracy. You talked about the stochastic process and the reverse stochastic process. And you gave a couple examples too, where we saw that briefly. For me, just, having seen the ultrasound of my wife and seeing that made me think of the noise that's embedded into those. And so I guess my question is this something that propagates into those fields of radiology, audiology, CT scans, ultrasounds, sonograms, Dopplers? Are you seeing that these areas are opportunities for this hybrid solver method?
Okay, that's an very interesting connection. So these generative modeling approaches do use diffusion processes, and there are interesting works that also vary this. So typically, it's really an ideal white noise, known Gaussians of different strengths, basically. But this is potentially varied, and there are some works that do vary this. You can also learn with this. I'm not aware of direct connections to radiology or so. Typically, where the connection is made, that you try to mimic these imaging pipelines with a model, potentially a simulator. But this is an interesting field. Right now, there's also many developments. Right now, as far as I have an overview of the field, these alternatives or more physically motivated diffusion processes don't have too much advantage over this simple white noise approach. But they're definitely interesting connections. I should mention here, this denoising process is in a way orthogonal to the physics remodeling. So in the examples I've shown, you have basically this artificial noise and the physics process, and they're really different space, different worlds, basically. And there are ways to potentially combine it, but this is quite experimental at the moment. I hope that answered the question.
All right, I'll keep it brief. You're talking about trying to scale up to larger systems and plugging into larger models like transformers and whatnot. But I know a lot of people on the call are interested in reduced order models where we sort of compress state space. So rather than working with little finite differences in state space, have you thought about doing finite differences and doing this kind of differentiable thing in a latent space?
That's also right. Reduced order models are a great point, and I should mention even the transformers in the end do something like this, right? They typically do reduce the space with some encoding into at least a lower dimensional space, but not a super small one. We have not done much on modeling in latent space. Main challenge typically is that in latent space you don't know anymore what the physics are, right? If we have Navier-Stokes, we know it's working in physical quantities. You need to decode, then you can easily apply the constraint. If you're in latent space, you don't know how to work with these quantities. The easiest way is to decode, then apply, and then backprop into the latent space. But this is potentially an interesting point, how to constrain latent spaces or work in these reduced ones. But right now, admittedly, in my group, we typically work on the physical quantities after decoding when applying the constraints.
Cool. Thank you.
All right. I think we'll call it there. Again, thank you so much, Nils, for this amazing talk. I think from the sheer number of questions and the diversity, you really see how excited the community is about this subject. So yeah, let's thank our speaker again. And I'm looking forward to seeing you again soon, Nils.
Right. Great to hear. Thanks for the questions and have a good day. Yeah. See you in Munich. Exactly. Bye, everyone.
Take care, everyone.
Bye.